Hello. In this video, I would like to show you how GIFMod's automatic parameter estimation or inverse modeling capability works using a very simple example. So the example I'm going to use is a batch reactor with a pollutant undergoing a first order decay. I have created this synthetic data set representing the concentration of a pollutant in a batch reactor over time, which I'm going to use. So what I'm going to do is first I'll create a model of the batch reactor, and then I'll basically run the model in forward mode, and then I'll run the model in inverse mode to estimate the parameters. Okay, so let's get it started. So the first thing is I need to create this batch reactor. I can use any other components as since there's no hydraulics in the model that I'm going to show you. It's just a batch reactor, so no flows. I can use any of the or a lot of the components here, but the simplest one is a pond, right? So I'm going to use a pond. The pond can basically represent also I don't know, batch system, a tank, anything when you have a kind of standing water somewhere, right? So I'm going to add this pond, and so I'm going to assume that the volume of water in the pond is 1 cubic meter. It doesn't really matter. So I'm going to set the bottom area of the pond to be 1, and then I'm going to make the water depth also to be 1, right? So so initial water depth is going to be 1. Since there's no hydraulics, the water depth is going to stay at 1, right? Next thing, what I'm going to do is that I want to add this constituent, right? I'm going to call it constituent A, okay? So in order to add the constituent, I'm going to click on this water quality item in the project explorer, and then I'm going to go to right click on constituents, and I'm going to add a constituent, right? So by default the name of the constituent will be constituent. I'm going to change it to, let's say, A, okay? Then that's all I need in terms of defining the constituent. So now what I have is that I have this constituent. Because I haven't defined any reactions at this time, this constituent is a conservative constituent, right? So now what I'm going to do is I'm going to add this reaction, which is pretty simple. But in order to add the reaction, I'm going to add this basically reaction parameter, which is going to be my decay rate constant, right? So I'm going to add a reaction parameter, and I am going to let's call this case KD, right? So KD is a decay rate. I'm going to leave the value to be 0 at this time. Then later on, I'm going to basically, because what I'm going to do is that I will treat this k sub d as an unknown parameter to be estimated. So I'm going to not worry about the value of the parameter at this time. I'm just going to leave it as 0, and then later when I define a parameter to be estimated, I'm going to assign this value to be equal to that parameter, right? So next thing, okay, so let me define my reaction network as well. So I'm going to right click on the reaction network, open reaction network window, and then I'm going to have only one process, and that's going to be decay. So I'm going to call the process decay. The process rate is going to be, it's a first order decay, so it's going to be KD times A. So A now represents the concentration of the constituent, and then the value here is going to be the stoichiometric constant, which is going to be -1, because my constituent A is undergoing a first order decay. Okay, so that's what I have here. Okay, so I'm going to close this window. Next thing, what I want to do is I want to basically say to the model, say to GIFMod, that this KD parameter, reaction parameter that I defined, is an unknown parameter that I want to be estimated, right? So I'm going to go to inverse modeling. I'm going to add a parameter. So add a parameter. The parameter, I'm going to call it, I want to call it a different thing than the reaction parameter that I defined right there. So I'm going to call this K underscore D, which is slightly different than the reaction parameter. Here I'm going to assign a value. Now this value, let's assign a value of 0.5. Okay, so this value, what it does is that if I run the model in forward mode, this is the value that will be assigned to KD. And then I'm gonna just essentially, in order to do the parameter estimation, I need to indicate a maximum and minimum value, sort of a bracket where the search is going to be conducted within that range. So the maximum value, let's say I say 5, and the minimum value I'm going to say 0.1, right? And since you see that the maximum and minimum values are kind of order, at least more than one order of magnitude different. In order to prevent the value of KD to become negative, I'm going to say I'm going to indicate the prior distribution to be log normal, right? So it's basically what it does is I'm going to do two things when I do the inverse modeling. We're going to do a deterministic inverse modeling using genetic algorithm. It's basically based on maximum likelihood. So that deterministic inverse modeling, what it does is that it gives us one value, the best value of KD that can match the data. And then the next step is what GIFMod does is that it does probabilistic inverse modeling using Bayesian approach. Now, when we use Bayesian approach, we need a prior distribution, right? So what this the prior distribution basically the way the prior distribution is determined is the model will basically build a prior distribution with a log norm, which is in this case log normally distributed, with a 95% bracket, or 95% if you want confidence interval of 0.1 and 5, right? So basically there's a 2.5% chance the value a priori is going to be less than 0.1, and then 2.5% chance that it's going to be larger than 5, right? We're going to go into that later on. I'm going to show you some graphs and so on, how the prior distribution looks like and so forth. Okay, so that's what it is. Now, next thing I want to say to the program that this KD is actually the value of the KD needs to be taken from this parameter. Okay, now in order to do that, what I'm going to do is that I'll choose the parameter, I'll right click on the value, and then a menu item called parameters appear here, and then I pick K sub D, and the value becomes K sub D, K underscore D, I'm sorry. So this is going to be the value. So what it says is basically anytime during the runtime that this value of KD is needed, it's going to be taken from the parameter that we defined here, right? Okay, so that's what it is. Now next thing, I need to do a few more things. I need to define some sort of, or introduce some observations. Okay, so which KD is going to be determined based on. Now, one thing that I haven't done yet is I have not assigned any initial concentration to the pond. So I have to say, okay, what was the initial concentration of my constituent A in the pond? So in order to do that, I just go here, I find the constituent initial concentration. I click here and I say my only constituent A has a value of, let's say the initial concentration is equal to 1, right? So the initial concentration is equal to 1. And now actually I can run the model in forward mode. Since I'm not, basically as long as I'm not running it in inverse mode, I don't need to introduce basically observations, right? Okay, so now I'm gonna first save what I've created so far. What I'm gonna do is that I will save this basically this project into a new folder, and the reason for that is that because when I run the inverse model, GIFMod is gonna create a whole bunch of output files, and I want things to be more organized. All the output files will go to the same folder where I basically save the GIFMod model. So things will be more organized that way. So what I'm going to do is that I'll create this folder here. Let's call it inverse example, and then I'm going to save the model as inverse example.gifmod. Okay. So now what I can do is that I can run the model in forward mode. Okay, so I'm going to run the model in forward mode. It's going to be pretty quick, and now I can look at the results. So one thing that I'm interested in looking at is the concentration of A. So just right click on the pond, you go to plot constituent concentration, and I click on A, and this is what you see. So as you can see, the contaminant is decaying. So next, what I want to do is that I want to actually do the inverse modeling. In order to do that, I have to introduce my basically observation data. So in order to do that, I'm going to go to inverse modeling. I'm going to do observation and right click on it, and I'm going to add an observation. So you can name your observation anything you want. I can just change this name to A_observed. Okay. Then I have to say what it actually is, right? So basically, the only location that I have is pond 1. I only have one block. Now, if you have a more complex model, you can have multiple choices of, where something is measured, right? We can choose a block or a connector. In this case, we only have a block. Then this error distribution is basically the distribution that the likelihood function is calculated based on in Bayesian modeling. So we can choose normal or log normal. In this case, I'm going to keep it as normal. And the quantity, so we have a number of quantities that we can pick. H is hydraulic head, storage, effective saturation, S sub E, evaporation, and so forth. But what I'm going to choose is A in aqueous phase, and that's the only phase that we have. So I'm going to choose A in aqueous phase as our observation data. Then I have to also provide the observed data. So I've created this synthetic observed data, which I'm going to use for this example. So I'm going to just click here. My observation data is saved in another folder. So it's basically called, I think it should be observed data.csv. So it's a CSV file with two columns. The first column is the time, and the second column is the values of concentration measured, right? So I'm going to open this. If I want to look at the observed data, all I have to do is to right click and then click on data, and this is what you have. Okay, so we have some measured data. This kind of noisy, as all observed data are typically, and basically the duration of the time that the observation data has been collected has been 3 days, right? So one thing I want to do is now go and change the simulation period to basically match this one. So what I'm going to do is that I'm going to go to settings, project settings, and then I'm going to change the simulation end time to 3. Okay. Now what I can do is that I can still run the model, and what that allows me is basically based on the parameter value that I provided, I can now see how the model and measured data match. Okay, so if I say plot model data, and this is what I'm going to get, right? So basically the red curve that you see is the model data, and then this is the model data corresponding to the concentration, and then the dots are the measured data. And as you can see, we don't have a good match, and that's something that is expected because we really didn't do any parameter feeding, and the parameter value that I entered was completely arbitrary, right? So now is the time to do the inverse modeling. Okay, so in order to do that, I need to set some parameters. So I'm going to go to the genetic algorithm, there are some default values of the parameters for basically tweaking parameters for genetic algorithm. For example, the number of generations is 50, and I'm going to keep it that way. The population that I'm going to use is 40. There's a mutation probability, and then there are some other tweaking parameters. Number of threads to be used, number of cores actually, and so forth. So then for the MCMC, I need to make some changes to make basically the results that I'm going to get to make them meaningful. I have to change some of the parameters. So what I'm going to do is this parameter is number of MCMC samples. 500 is really not adequate, so I'm going to change that to, let's say, 50,000. So I need I'm going to take 50,000 MCMC samples. Then I can also specify the burn-in period, which so I'm gonna throw away the first 1,000 samples, and that's pretty much it. So so let me just go and save the model again, and now is the time that I can do the inverse modeling. So in order to start the inverse modeling, I'm going to click on this button with this gentleman or woman running backward. It's supposed to indicate inverse modeling. So so I'm going to just click on that, and then this is going to take some time. So I'm going to cut some part of the video. So this one I'm actually doing the genetic algorithm, and now this is it's doing the Markov chain Monte-Carlo. And let me explain a little bit what these what you see on the graphs are. So the top graph shows the perturbation factor. Okay, so it's basically how much perturbation we are applying in our Markov chain Monte-Carlo search. And then the bottom one shows the acceptance rate. So we try to keep the acceptance rate at a certain given value. Here, I guess it's something around probably 0.2. So anytime the perturbation factor goes below the threshold that is provided, the acceptance rate goes below the value that is provided, the perturbation factor goes down, and vice versa. Okay, so this is going to take some time because we are essentially running the model 50,000 times. It's a very simple model. So so basically, even running it 50,000 times is not going to take that much time. But of course, if you have a more complex model with more parameters, and the simulation time of the model takes longer, this analysis may take much longer. Sometimes, I don't know, sometimes more than days or so on, really depending on the complexity of your model. Okay, so when we reach to 100% of the Markov chain Monte-Carlo sampling, there's still a wait time. Basically, this is the time that it takes for GIFMod to perform some post-processing of the results, including generating some realizations and so forth. So you're going to see this not responding on your window. It's going to stay for a while, and then you have to wait for this to go away, and then we can look at the results. Okay, so now it's basically the inverse modeling is completely done. As you can see, it took 215 seconds, which is not too bad, and that's because the model was quite simple. So I'm going to close this window, and then we can look at some results. So the first thing, basically, you may want to see what was the optimal value of the parameter that was estimated. So if you now click on the parameters, if you remember, I put in a value of 0.5 for KD, and the value is now changed to 1.55113. Okay, so this is the maximum likelihood estimate of parameter KD. So now if I run the model, it's basically, or save the model, I'm gonna have the the optimal value assigned to the parameter KD. Some other things I can do, if I right click on the value of KD, I can look at, for example, the percentile. Now this is not very good. So basically a better way is that I right click on the parameters, and then there is this menu item that appeared here that says plot percentiles, and I can click on that one, and you can see, the range of the parameter KD is quite narrow. And then we have another parameter that was just added automatically, and that's the standard deviation. So this is the range of the standard deviation, and then we have the range of the parameter KD. Okay, I can look at the posterior distribution and prior distribution. So if I look at the prior distribution, this was our prior distribution that we provided. Essentially, it's a log normal distribution. And then we can also look at the posterior distribution. So this is the posterior distribution that was inferred. So as you can see, the posterior distribution is quite close to a normal distribution. I can compare my posterior and prior distribution. So this is my prior distribution and posterior distribution. I can copy the posterior and then paste it on the prior, and that's what you see. So this is the green shaded area is our belief about the distribution of the parameters before applying the data, and then after applying the data we got this narrow normal distribution. Next, we can look at the observed data. Let's see how good the modeled and measured data matches. So if I click on plot model data, this is what you can see. So this is our model data now, or our model result now matches the observed data quite well. I can also look at some other things. So I can look at the agreement plot. So if I click on the agreement plot, you can see, this is basically modeled versus measured, fed by a 1-to-1 line. So as you can see, it's pretty good. And I can also look at maybe 95 percentile of predictions based on the posterior distribution of the parameters. So you can see this is actually not 95%. It's basically have different percentiles, and so this is the bracket of predicted concentrations versus time based on our credible intervals of the parameter values. I can zoom in and you can see a range. We can look at in this case this is not very interesting, but if you have multiple parameters and there may be some correlation between the parameters, we can look at the correlation matrix. So if, basically now in this case there's very small correlation between the standard deviation and the decay rate, but sometimes correlations may be significant. So that's pretty much it, and then we can also look at some basically, if you want to take the data and do some additional analysis, basically if you go to the folder where the model was saved, you're going to see a whole bunch of results. So I'm gonna go through a few of them. For example, if you want to see how the genetic algorithm worked, you can open this file called GA-out. So if I open it, so this is what you have. We have generations. With each generation, we have 40 population, and these are the parameter values in each generation and for each individual of the genetic algorithm. So the first column is just essentially a counter. The second column is the parameter value of the KD, and then we have the standard deviation. That's going to be another parameter that was just added automatically by GIFMod. And then you have the likelihood, and then at the last column we have the mean squared error. So So basically what you have is at the end we have the value of the parameters, so you can look at the optimal value of the parameters here. Another thing that we can look at is there's this file called Mcmc Output. This shows the basically the result of the Markov chain Monte-Carlo. So basically these are all the samples. So essentially you can take this and create your own histograms of the posterior distribution of the parameters and do all sorts of other analysis on the raw data. And that's it for this video. Thank you for watching, and if you have any questions, feel free to contact me through my email or post a comment or question on the GIFMod website. And have a great day.